Alright, so let's get started with the last couple of sections. Well, there's one more besides, I remember, differential equations. So today we move on through chapter 12. It's polar coordinates on 12.2 and 12.3, the calculus in polar coordinates. Well, so we're going to look at a new system of floating points, which is, well, it's called the polar coordinates, and we are going to see the relation between that polar coordinates and the Cartesian coordinate system. And we're going to do some calculations here and there. We are going to convert equations from polar to Cartesian and vice versa. And we're going to look at the graphs in polar curves as well. So these graphs are pretty interesting, actually. These are going to be graphs of like flowers, hearts, spirals, pretty cool stuff. So, okay, so what is the polar coordinate system? Well, so you can think of, well, let's describe again what Cartesian system is. So the Cartesian system is simply the system, the XY system. You know, any point X, Y, they're called order pairs, well, because it follows the order X and then Y, all right? So X in the horizontal direction and Y in the horizontal in the vertical direction. Now, for the polar system, however, well, yes, the axes are going to look like, you know, rectangular. However, in this case, we're not going to plot X and Y, but we are going to plot in terms of a radius and an angle, for example. So you can think of, okay, let's face towards the positive x-axis, and how far it's going to be the distance or the radius. And if we start panning counterclockwise direction, that's going to be our angle. For example, in this case, the points are going to be r comma theta as opposed to x comma y. All right, so, and in this case, well, the horizontal axis, well, in the Cartesian system, it's the x-axis. Here it's called the polar axis, and we are going to have an origin as well in the polar system, but it's not going to be called the origin. It's going to call the pole. Okay, which, yes, it's also 0, 0, a radius of 0 and an angle of 0, you know. So, and let's see. So let's look at a couple of examples on how are we going to plot these points. Okay, so number one, let me add the x-axis and the y-axis in a way. Well, so notice in this case, these circles we have well, more circles. Those every new circle represents a distance or a radius, and here we have the angles. I think this is 15, 30, 45, 60, and 75. I think, and then 90 degrees. Okay. So we're going to plot this point in polar coordinates and represent their location in at least two different ways. So that's something pretty interesting as opposed to the Cartesian system. So, okay, let me use this color. So in this case, we're going to go from the pole. We're going to go 3 units. Like we're plotting x, but in this case it's a radius of 1, radius of 2, radius of 3. That's r, and that's theta. So from here, and then we're going to pan this to 60 degrees. All right, so the point will be here. And you might want to draw a line between the pole and the point. I think we're going to need a darker color here. Okay, how about this one? Alright, so that's the point. 360 degrees. Alright, so for now, of course, we are going to leave it in degrees. We have another example right next to it in radians. Okay, so, well, that's the representation of this point, a radius of 3 and 60 degrees in the polar system. Now, here's the thing. We can represent this point in pretty much infinitely many ways, as opposed to rectangular points. For example, well, let me use the same color. For example, the point 3,5, 3,4, 2, 3, 1, 2, 3, 4. All right, so that's the point 3,4. Can you represent the point 3,4 in another way in the Cartesian plane? I mean, is there another 3,4 besides this one? It's unique, right? There's no other way to represent the 3,4 in the Cartesian plane. However, points in the polar system, because they are related to the trigonometric functions, sine and cosine in particular, recall that those functions are periodic. In particular, they are 2 pi periodic. That means that from the point, if you go around 2 pi, you're going to get back to the same point. Add another 2 pi, you get to the same point, and so on and so forth. All right, and well, that's what we're going to do in this case. Well, so let's see. If we go around one more cycle, we're going to get back to the same point. It's still the same radius. But what would be the new angle if we add 360 degrees?
420.
Or 120 degrees, all right. How about we do a second turn?
780.
780, all right. Or we can also go backwards, well, not backwards, but rather clockwise instead. So let's go back to 360. And so instead of adding 360 degrees, we will subtract 360 degrees. That's going to give us 3, and I believe it's negative 300 degrees. And how about another one? I believe it's negative 660. All right.
630.
630. Did you guys? Negative 660. This looks like an 8. Okay. So yes, we have 1 to 5 representations of the same point. All right, let's do more. And typically this is like the tricky way to represent, and it's important to take it in consideration because in Calc 3, when you look at this type of points, this has to do with the direction of some vector related to its angle and length. Well, you'll see when you get to Calc 3. So we can transfer this point, so to speak. You can think of having a mirror right here and send it over here. What would be the angle here? So from here to there is 180 plus 60, 240, so 240 degrees. But notice it's collinear with the angle with the point that we plotted before. However, what's the difference? The difference is that this point in green is in the opposite direction as the point in purple. Well, to fix that, yes, it's still 3 units, but because it's in the opposite direction, we need to change it to negative. All right. Now, can we represent this in infinitely many ways? Well, of course we can. So, for example, if we add, negative 3, the radius remains the same. 240, let's go around one cycle, one turn. That means add 360. That's going to give us 600 degrees. And if we add another turn, add 360. That's 960. And well, let's not add too many. Now let's go and subtract. So what about 240 minus 360? to get back to the same point? Well, that means -3 still. And is that -120? And one more. -120 minus 360, -480, I think. All right. And I mean, we can go on forever, but we don't have to. I mean, what we want to take from here is that, well, polar points in the polar system can be represented in infinitely many ways due to the periodic properties of the trigonometric functions that are related. Well, we'll see about the trigonometric functions soon. And well, this doesn't happen with points in the Cartesian plane because they're rectangular coordinates, x and y. Those are not periodic, okay? So let's look at another example where 3 and 3 pi over 4. Well, 3 pi over 4 is located, number 1, 3 pi over 4 is located here. And, well, I'm just going to refer to the point. I'm going to write the equivalent versions here. All right. Is there another way to represent, or what is, actually there is, but what is another way to represent? So in this case, well, we're not going to add 360. We already did it in degrees in the previous example. Let's do it in radians. So in this case, we would have to add how much to get back to the same point?
2 pi.
2 pi. Okay, what do we get when we add 2 pi to 3 pi over 4? All we have to do,
11 pi.
It's, did you say 19? 19 pi over 4? Yep. 11? Oh yes, it's 11. 11. Well, actually, 19 is another. 11 pi over 4. And yes, that's a 19 pi over 4. And I mean, of course, we don't have to do too many. Just a couple is fine, and of course backwards, or rather clockwise. Instead of adding, let's subtract 2 pi instead. -5 pi over 4. No need, when adding multiples of 2 pi, no need to add the pi symbol on your calculator. Just get the 3/4 and subtract the 2. Whatever you get, keep subtracting 2, and then just add the pi in the end. Okay, so that's the next one would be 3. I have -13 pi over 4. All right, -13 pi over 4. And of course, we can do the same that we did by reflecting the point in the opposite direction. And number 1, well, this is to fix the issue with the direction, you need to change the sign of the radius, and the angle will be, in this case, I believe that's well, there's a couple of ways to describe this. However, I'm gonna go with initially with -pi over 4, right? But of course, if you add 2 pi, that's 7 pi over 4. And keep adding another 2 pi, 7/4 plus 2. I have 15. Oh, come on. 15 pi over 4. All right, and I mean, I think from here, we don't have to go back and do it clockwise. I think you see the picture of this, right? So that's ultimately what we want to get from here, that in the polar system, we can represent this same point in infinitely many ways, right?
For the point -3, -pi over 4, do we use negatives on both, or just the radius? Or just the radius?
Just the radius.
Oh, okay.
Just the radius. That's the only one that changes sign, because that's to indicate that the actual direction is in the opposite direction. Yep. All right. How do we relate between polar and Cartesian coordinates? Okay, so here are the formulas to convert from polar to Cartesian and vice versa. And I mean, these are, like I mentioned before, the polar system underlies on the fact that we are looking at circular functions. And well, where are the circular functions coming from? Well, that in relation with radius and angle. Basically, well, not the unit circle, not just the unit circle, but actually a circle of any radius. You know, if you might remember from when you first learned this in trigonometry in general, arc, cos, theta. Use a different color. R cos theta, R sine theta. Those are the points, the form of the points in a circle of radius r. But then they just told you, okay, we're just going to use the unit circle. That's simply cosine sine. All right. So, but in this case, well, we're going to look at points that are not just a distance of 1 unit away from the pole, but other distances. And then, so here are the formulas, and then the formulas to convert from Cartesian to polar. Well, we're going to use the Pythagorean theorem. Well, we will see how this is related to the Pythagorean theorem, and well, you'll see. Okay, so for example number 2, find the rectangular coordinates of the point with polar coordinate 6, pi over 6. All right. So all you need to identify here is what is r and what is theta. So in this case, recall that the first number, in this case, is the radius, and the second number is the angle theta. And well, x equals r cos theta, and r and y equals r sine theta, where r equals 6 cosine pi over 6 and 6 sine pi over 6. And well, this is just basic trigonometric calculation. Pi over 6, which is square root of 3 over 2, and 6 times sine of pi over 6, which is 1/2. This reduces to 3 root of 3, and this is 3. Right? So from here, we say that the point 6 pi over 6 is equivalent to 3 root of 3, 3 in the rectangular system. All right? Pretty easy calculation, just plug in the numbers. If you're using your calculator, well, actually you will be using the unit circle, so you get the exact values of the trigonometric functions, unless otherwise stated. Typically in applications to physical situations, well, we prefer decimal, so we can have an idea of what the magnitudes are, or what the velocities, distances are in a more or an approximated way. Let's do the reverse. Find the polar coordinates for the following. So number 1, my advice when going backwards is to first plot the point, because typically we can get the same angle for different points if we don't know. But if we don't know where the point is located at, we may get the incorrect angle. So let's see. So the point 1 root of 3, well, that's located here, 1 root of 3. All right, this is going to give rise to, if you will, a right triangle. Okay, so, well, number 1, we need to find two things. Number 1, how far is the point away from the pole? That is finding the distance. And if we look back to the formula at the top of the page, this looks like the Pythagorean theorem, or like the distance formula, where one of the points is the origin 0, 0. Right, then we're going to find the angle by using tangent theta, which is opposite over adjacent, which is really finding the inverse tangent, as we did at the beginning of the semester when we computed inverse trigonometric functions. So number one, let's find the radius r, and the radius r is r equals the square root of x squared plus y squared, and that's the square root of x, which is 1 squared, plus the square root of 3 squared. So that's the square root of 1 plus, be careful, the square root of 3 squared, the root cancels the power 2, 1 plus 4, and this is 1 plus 3, which equals to 4, r equals to 2. All right. And well, there's a couple of ways, of course, to get the angle. I mean, typically these type of exercises are going to give you points x comma y, in which you can relate it to either the special triangles for finding the trigonometric functions and therefore getting the angles, or anything like, that you can relate to the unit circle. So, and in this case, well, I think the 1 and the root of 3 gives us an idea of, for example, if you divide this by 2, this is, I believe, 60 degrees, isn't it? Or pi over 3. So, or you can do it, of course, theta equals arctan of y over x, which is arctan of y, which is root of 3 over 1, and this is pi over 3. All right. So this means that the point 1 comma root of 3 is the same as saying a radius of 2 and an angle of pi over 3. All right.